So, okay, as I said, PCA, I wanted to go a bit into the mathematical background of PCA and how it works and why we use it. So we look a bit at the math and then we'll try it out and then we see where we go from there. To remind everybody why we want to use PCA, let's have a quick look actually at the homework that you have prepared for, that you might have looked into this time. Anybody has given the homework a try? Okay, a few people. So, and this point of the second homework, which we'll talk about more tomorrow, was of course for you to go through one is the standard starting analysis. And I'm aware that we still haven't got much to the biology, but we're still getting familiar with the data. But yeah, that's how we do it in math. You first go from the basics and then the interesting stuff comes later. And here we had this, the general idea that we start off with our count matrix where each cell is described by a vector which gives us in each of its components the counts, the read counts for one gene. So a cell is described by a vector with several thousand components, and we might want to say that these several thousand components, that therefore these cells live in a high-dimensional space, which we may want to call the expression space, because each component is the expression strength of one gene. We do some metric change in this expression space by doing this log normalization, and then we run into the issue that actually the space is probably way too rich and over-dimensioned in order to describe the cells well. And we want to do what we call a dimension reduction. We have data with a very high amount of features, and we want to reduce it to a lower amount of features, which hopefully doesn't merely condenses the information rather than selects it and removes information. And as you've seen, we have done a multiple step dimension reduction last time. First, we started from all the genes down to only 2,000 baby genes, which were the highly variable one, where the noise went beyond the Poisson noise. Then we went down from these through the PCA into a 50-dimensional space. And finally, we went from this 50-dimensional space with the humor projection into a 2-dimensional in order to have something which we can visualize on the screen. Now, principal component analysis is used in very diverse areas of science. And so this application here to single-cell data analysis is just one of them. And sometimes, or in my opinion, pretty often in mathematics, you find that it's easiest to understand the concept if you understand where it comes from. What were the original questions, why this concept was introduced in order to solve which problems originally. So I will now explain PCA, not talking about single cell, but talking about one of the original applications, the one that's convinced people that it's a useful mathematical concept, and that one comes from psychology. In psychology, there is this idea of behavioral of personality traits, that the personality of a person can be understood along different axes. Anybody who ever had the questionable experience of using a dating platform in the recent 10-15 years knows all this pseudoscience about this four-letter qualification where the profile starts with IM and IJNQ, and you have to look up in some table what it is. Those who don't know what this is, you're lucky. And this is considered pseudoscience, but not really. It just misses the crucial part, because there's a real science behind it, which I want to tell you now about, because it is a very nice example of scientific computing of data analysis in science, and how math is used in, well, in that case, not biology, but psychology. There's something which the psychologist calls the Big Five. And let's have a, my mouse doesn't work. Let me try with this here. Maybe that works better. No. Just one. What's wrong now? Seems my other USB port is in a bad mood today. Okay, the big 5 personality traits is the idea that human personality can be quite well described by giving a quantitative assessment along these 5 axes, which you have here, which you have to consider as a continuum along 2 extremes. So, for example, here this axis, which is called extraversion, of course, goes from a very introverted to a very extroverted person. Or with agreeableness from a very quarrelsome to a very harmony-seeking person. Openness means the path from people who are sort of very closed-minded, try to stick to their little world, versus adventurous people who want to go out and explore everything. Conscientiousness refers to the ability to be detail-oriented, but also have a conscience, try to consider one's impact on other people, etc., versus people who just don't care about others. Neuroticism is the one which we really don't have a good name for. The opposite acts, maybe well balanced against what in popular talk one might consider unhinged. You already noticed from my difficulty of describing these properly that there's controversy because there seems to be moral judgment in how we describe these things. So we should really understand where they come from and why psychologists think that we have 5 of them and what the point and how we define it. And we will see in a moment that the interesting part is that we first have data, and then we try to describe our data, and these words come out of our attempts to give a verbal description to something which before we see in numbers. So, I might have ruined my mouse by pouring this. Does anybody have a mouse by any chance? Because I always find it terribly hard to use a touchpad. Oh, let's see, have I already put this up here? No. And na verdammt. Where have I put the PCI chapter that I prepared for you? Here. Just a second, I'm feel a bit unable now to work properly without. Why can't I open this? Sometimes this computer, this R makes life really difficult. Okay, it should have opened it here. Site ECA math. Open in web browser. So, okay, the starting point of this whole thing is that psychologists in the 50s and 60s, already starting in the 30s, got into this idea of trying to mathematically quantify personality, and their idea was that they made lots of questionnaires where we had a couple of questions or statements like the one I've written here. I don't talk a lot. I am interested in people. I leave my belongings around. I'm relaxed most of the time. And the subjects are then supposed to answer along what we call a Likert scale or Likert scale. This is this usual scale with 5 buttons where you have, they can say, yeah, this doesn't fit me at all, that not really fits me, that may not fit, that fits well, and that clearly describes me. And along this axis from -2 to +2, you describe your thing. And you get a questionnaire of a long number of things. And over the years, psychologists have amassed here this big item of thousands of different questions. And now you can imagine that many of these questions probably go into the same thing. Somebody who says, I like to talk a lot, is somebody who might also agree with the statement, I'm really always the center of a party, to give 2 examples, standard examples of things which go along well. So once we take all this data and put it together and try to look and ask many thousands of people to fill out our questionnaire, we can ask which questions might be correlated and which questions might not. And then we might come to the conclusion that at the moment each of our test subjects is described by the answer to these several hundred questions, but in reality we should be able to condense this down to a much smaller number of features or of personality components or personality traits, such that we can predict the subject's answer to questions from these predictions, from these individual values. So now, so what we do here is, I've written this down a bit so that I don't mess it up. As I just said, it stands to reason that many of these questions give correlating answers, and we now posit that the human personality can be quantified along a rather small number of axes. And each of these axes is a direction, like introvert to extrovert, or very careful to very adventurous, or something like this. And we now consider these axes as directions in a Euclidean-like space, which we call the personality space, and where we now assume that we can describe the human's personality as a vector in such a space. And so let's assume that this space has chi dimensions, and hence we can embed this personality space or make it isomorphic to an embedding into R to the k, and then we can describe each subject by a vector with k components, which I call x. And of course we have the answer that the subject number I gives to the questionnaire item number j. And once we have fixed our basis in our personality space, because remember at the moment we have come up here with these axes like introvert, extrovert, careful to adventurous, or something like this. But we don't know yet whether these different directions are orthogonal, or whether they are sort of collinear in the sense that somebody who's high in one thing also tends to be high along the other thing. And you can imagine, if you consider this geometrically, it's basically the question whether these two directions, which are two traits, like these ones here, are orthogonal, like it is what you have, whether you're high or low in this axis has no bearing on how you're along the other axis, or whether they sort of have an acute angle, like the scalar product is not zero, which implies that the answers which gave rise to these directions are correlated. And we put this together now by saying, we assume that we have a space, and at the moment, as usual in linear algebra, we assume that this space is just an abstract space which doesn't have a basis yet. And we will have to fix a basis later. But for the moment, let's assume we have already fixed a basis so that we can write down this personality vector actually in actual components, x1 to xk. And if we want to predict the subject's answer to one of our thousands questions, as you already know, we will later find that k equals 5 is a reasonable number to assume. And then we might say, if I know a subject's answer to a subject's personality vector, then I can predict what the subject will answer to question number j by multiplying, making such a linear combination where AJR is the strength and direction of the influence of a personality dimension R onto a subject's agreement with the questionnaire item J. So if A is positive, then this means that subjects which have high score in the personality direction XIR, they tend to agree with the statement J. And if it's negative, it means they tend to disagree. And if it's around 0, it means that this direction doesn't have an influence on the subject's opinion of that. Obviously, we have to think about what is the offset with y0, which is what a subject has. We imagine we have a zero subject. The zero subject is a person which sits at the origin of his personality space. And as we can at the moment imagine this personality space as an affine space, we need to fix not only a basis but also an origin. It makes sense to put the origin on what we might call the average person, who in all these personality traits is sort of in the middle. And this average person, for each question we can ask what would the average person to this question say to this question, and then we get this offset yi0, which basically in the end means whether this is a question that people tend to agree or not. You can imagine that a question like I like to murder people has very few people agreeing, so it has a very strong negative offset, while a question I like chocolate ice cream might have a very positive offset. So this is our general idea, and you can already see we're using now pretty basic linear analysis terminology to actually make sense of this, and this will work surprisingly well. So what we also now do to make our life, all right, I've already said that, we now assume that our personality vectors are all standard, so we have placed the origin such that the average person sits in the middle. And let's also make clear that this prediction here just gives us an expectation value. The actual answer of a subject to this question will of course be the answer that we predict plus some random noise, which can capture two things. A, it can capture aspects of the questions which are not well predicted by our model of personality, and B, it just makes random fluctuation because the same person will not always answer the same way to a question depending on the mood of the day or whatsoever. So we consider this just a noise term which we for simplicity say is normally distributed. As I said, we can now also say, I've said we center the subject so that the average person is in 0, but we can also center the questions. At the moment, I said the questions are simply scored. -2 is strongly disagree, 0 is can't say, 2 is strongly agree. But I can subtract from this the average answer of all the questions, of all the subjects to this question, so that 0 is not I neither agree or disagree, but 0 becomes whatever the average person might say. That has the advantage that we can drop these offset terms, so we implicitly assume that for each question we have figured out the average answer of the people on this question and subtracted it from the answer score of each subject, so that now the averages are 0 and hence all the offsets can be dropped. This is of course useful because we want to use linear algebra, and you know in linear algebra the moment you go from a vector space to an affine space you have to deal with all these lines which don't go through the origin anymore, and that always makes life difficult. In statistics, this is a pretty common thing. They call it centering, which means whenever you want to do any calculation, you first subtract the average, so that the average is 0, and this allows you to then drop a lot of constant terms which actually only clutter your notation. Now, if we now write yi for vector formed by subject I, when we can say yi describes the whole questionnaire filled out by subject I and hence includes everything that we know about the subject's personality. And so it's an n-dimensional vector in VR to Vn. And we can assemble the answers of all our m subjects which have filled out our questionnaire into a big matrix which I call capital Y. And the rows of this Y matrix are the subjects and the columns are the questionnaire items. This, by the way, will cause us a little bit of confusion. Whenever you have data matrices, there's always the question of whether what are rows and columns, and the convention in statistics is that the units of observation, so in our case, the subjects, the different people who fill it out, they are the rows. And the different questions or features of different things that you can measure, they are the columns. But there are plenty of reasons where the writing down, where the notation becomes easier if you transpose that. So you will always get confusion about which way around it is this time. And you see this has already happened to me. I have here these yt. Because what I now do, I want to write this equation that I have here as a matrix equation. And then I have y is my vector of answers, x is my vector of personality scores. So each column of X is, each row of X is one person described by its 5 or 6 personality values for these 5 or 6 dimensions, which we haven't really fixed the basis for yet in this personality space. And A, the loadings matrix, tells us how strong the influence of each personality component is on the answer, predicted answer of each question, either positive or negative. And so once we now have done our analysis, we have got this, done our survey and asked lots of people to fill out our questionnaire. And to go ahead, to remind you of this, in the questionnaire we have tried to put a lot of such questions like this one here. And we try to be as imaginative as possible to capture as many different aspects that we can think of in terms of personality. And of course, if there's an aspect of personality that our questions cannot really interrogate, because we forgot about this possibly because we weren't too sufficiently creative in coming up our question, our personality space will lack a dimension which is there, but we are blind to it. So, what we now do is we now say we have this question, this matrix Y, which we got from our survey, and now we want to infer matrices A and X. And this is a bit an issue because we want to decompose Y into a product of 2 matrices A and X. And we want to do this in a sensible way. And the way how we find a sensible model is to first realize if X, the personality space, really has a much lower dimensionality K than the number of questions N. And you see here, this is a linear map. When this means that if we for a moment ignore this error term and imagine this would be exact without the E, then the k-dimensional personality will be mapped into this question-answer space, but it will be all mapped into a k-dimensional subspace because A as a linear mapping can only map a k-dimensional vector into a k-dimensional subspace. So even for Y spans n dimensions before the n questions, the subspace should only have k dimensions. And we let us call this subspace S. It's the subspace spanned by the image of A, if you put in all of X, or actually by the columns of A. And we want to find this subspace now. And now what happens if we have E, our error term, and our error term means that to each, put it that way, the predictions for what our subjects will answer to the question now all sit on a linear subspace of dimension k in our big space of possible answers, and we have many points in this subspace, but the moment we now assume that the subject will not always answer as expected, but sometimes deviate from this a bit, we realize that the points with the actual answers will be close to the subspace, but not on the subspace, but not too far from it. So in a way, the subspace has been broadened a bit by adding a bit of Gaussian noise in it. So that now the manifold filled by it is actually n-dimensional and no longer k-dimensional. But if we were to project all these values back onto the subspace S, it's k-dimensional again. And the trick here is, so the picture that you should have in your mind. This is the subspace spanned by all the predicted answers, and the actual answers sit a bit outside of this. So if I look at this from the side, they sit around this thing here. And of course, in practice, I don't know the subspace yet. I only have here these points, and I have now to say, what is the subspace? I have to find it. And the way how I do that is that I say, I want to find that subspace such that if I project the points onto it, I get as little change as possible. So we can say, if we assume that the subject I has given these answers, the answers are the projection of these answers onto the subspace plus the orthogonal part which we haven't. So if this is the answer, we project it onto it. And let's say here's the origin, when the answer vector is first that one, and afterwards is this one. And we want to find now a projection, a subspace such that this information loss that we lose by the projection is as small as possible. So we say we are looking for an operator P, a linear operator which just projects each point in the n-dimensional space onto the subspace S. And as I say, this means that the vector I is decomposed in the image under projection, and we offer the part that we lose, and we want to lose as little as possible during the projection. So we want to find a subspace S with its projection operator P, such that we minimize here the amount of stuff that we lose here. And as usual, we use the least square criterion, so we don't minimize the length of a vector, but their squares. Which then simply means we add up over all the questions and all the subjects the difference between the predicted answer and the actual answer squared. Instead of minimizing this part, we of course can also maximize that part. So that would mean we want to maximize this here with an S instead. An elegant way to write this is to say, if I apply the projection operator not on each column of y separately, but on all the columns, then of course I get the matrix P times yt, which now simply is made up out of all these columns here. And we want to minimize again the sum over all the matrix elements squared, because that's the sum of the square of all the column vector lengths. And typically you write this by putting the matrix and putting a little f at the index. That means Frobenius norm, and the Frobenius norm is simply defined as the norm, as the vector norm, which you get by squaring all the components of the matrix and adding them up. And yep, of course here I have a square root, because the norm is of course defined as square root, but what I want to optimize here is the square of this norm. So simply the sum of all the matrix elements squared. So we're looking for the projection operator P, which maximizes this thing squared. The Frobenius norm is an interesting norm, because on the first hand it looks terribly coordinate dependent. But if you transform the matrix, the linear operator, you write it down in another basis, then the Frobenius norm will stay invariant. So even though it's defined on the components, a short calculation shows you that it's invariant under any orthonormal transformation of a matrix. So, continues on blackboard. Exactly. Now this is the point. Now I want to show you how we get the optimal projection vector P, or the optimal subspace S, in order to maximize this thing. And yeah, last year I've written this on the blackboard and made a picture. Now I'll write it on the blackboard again, because I didn't find time to take it yesterday. Display. Very good. So, just to remind us, we have we have a data matrix. Matrix Y with columns yi. And just because we will need this a lot, I will keep here a list of what our index means. So Y are the subjects, so the people who answer this. So each column is now a subject, and the rows are the question. You note this, my Y is now the opposite of what I've written in my on the projection, because I don't want to turn around the T that I just had. Remember, up. Where was this? Here I've written YT up there at the very top, and now I want to drop the transpose sign, and I want to go in with what I've written last time, otherwise I get confused, so please accept that these are now the colors. So, and Y is centered. That means that if that for each question with, so J are the questions, or the questionnaire items. And to be a bit more general, instead of subject, we can also say observations. And instead of items, we say features, to use general machine learning technology, terminology. Now, what and we want to reduce this matrix to a k-dimensional subspace such that our information loss is minimal. So we look for subspace S element Rn. So S is a subset of Rn, and projector and a projector into the subspace, a linear projector. Such that the projection loss is linear. So what we do is, as we said before, we decompose our yi into a projection part, pyi, plus n delta yi, which is the part which is orthogonal to it. And this effectively means that we take our space of possible question answer and subdivide it into a direct sum of our subspace and its orthogonal. And we want to minimize, our goal is that we want to minimize the projection loss. So that the projection loses as few information as possible. So this sum should be minimized, or equivalently the sum of the projected things should be maximized. So, and to do this, let's now look at this thing here. And of course, and to do this, what we now do is we write a basis for S. Fix basis for S. And I call this basis P1, P2, PS, PK. So S will be basis vectors of S. So this we just fix the basis, and what we will now afterwards need is that we have to see how do we select this basis. So we take our matrix and expand this projection thing in the basis. So this is, of course, so you see, we assume that this basis here is an orthonormal basis. So I can simply write pyi, I can simply write as, maybe I'll write it here on the side. I have now expanded pyi as a sum over all the f of some as I have expanded this thing in the basis PS, and the components, the coefficients in this expansion are of course the scalar products of this with this. And if I now want the length of a vector, I have to take these things, square them, and add them up. This is why this leads to that one here. And what I now do is I write this here as, I write out this square as follows. YIT PS BSTYI. So what I've done there, for those of you who are not, now I've lost my only piece of chalk. This. This is scalar product, so of course it doesn't matter whether I write PS times YI or YI times PS, so I can write ones like this and ones like that. If I write it either way, oh sorry, this was nonsense, I have to write it the other way. PS TYI YIT PS. And if I write it that way around, I now see this thing here in the middle, this part here together with that. This is this thing here, YI times YIT. And if you think about this a bit, you will realize that this is actually the matrix product YTY. Right, it requires a little bit pointing in this. You might know the usual thing. If I write vector times row vector times column vector, that's a scalar product. But if I do column vector times row vector, that's what we call an outer product, where basically each element of a matrix that we produce that way will be a product of one of the components. So we have in the top left of this matrix is the product of in element x comma y of this product matrix will be the x component of a vector times the y component of a vector. So we take the product of every component with every other component and arrange it in a matrix, and that's the outer product, and this outer product has this shape. And we will later see that this thing is not only is not only just some matrix, it's actually the correlation matrix of our data, and that will be crucial. But for now, we simply use it as a mathematical trick to write the whole thing as this here. TS from T times YTY times PS. Now, as you can see here, this construction here, with a quadratic form. We have some quadratic form given by this matrix, and you remember how quadratic forms work. Quadratic forms are functions which take a vector and map the vector in the underlying field, so in this case into the reals, such that it has this quadratic ability that you it's basically a bilinear form where you go in from the same part. So the crucial point is the quadratic form arises whenever you have a matrix, a symmetric matrix like this one. You can see that this matrix is symmetric because if I transform it, I again get YTY, because transforming means not only replacing all t's with non-t's but also reversing the order. So this thing is symmetric, and we have now a symmetric matrix where we multiply the same vector from the left and the right, and that's called the quadratic form, and we can easily calculate from the linearity of this thing in which sense it is quadratic. The physicists among you might have already seen quadratic forms a lot. You know it, for example, as the inertial tensor out of classical mechanics. So, and our goal is now, we want to now maximize, remember our goal was to maximize this whole thing, so we want to find a quadratic form such that it's maximal if we put in all these vectors PS. So, what I now do, in order to write this out, I now do an eigendecomposition of YTY. This means, and we write this eigendecomposition as follows. We write UL for the eigenvectors and lambda L for the eigenvalues of YTY. So this means that YTY applied to its eigenvector UL is lambda L UL. Let's add to my indices. L are the eigenvectors X of YTY. So, and we want to now choose a P1 Now what we haven't said yet is what's the dimension of our subspace. Do we want to have a 3-dimensional, 4-dimensional, 5-dimensional? And we will make induction. We will start with a 1-dimensional subspace. Step 1, find 1D subspace. So this 1D subspace is of course specified with a basis with just one vector, and P1 is the vector which tells us the direction of the subspace. So we project onto the vector P1. What P1 do we have to choose to maximize this? Which P1 maximizes remember, we want to maximize this thing, and this thing is this quadratic form added up over all the things. And at the moment we have only one here. And it's easy to see. We just write in Q on P1 is and of course, because this quadratic form is now P1 times this thing times this, So if we go over all the eigendecomposition of this, let me write this here first so that we can see this here. So this means now that we can write this quadratic form Q that we have up here applied to some vector P, like here, as P, T, Y, T, Y, P, which is, of course, YT if we now expand. I'm running out of space here. So I have to do this now. I have to expand P in the eigenbasis of, you have space right on your thing, so I can flip this in and then I flip it out again. So we want to calculate Q of P as P T Y T Y P. And for this, expand P in eigenbasis of Q, or the eigenbasis of YTY. And this eigenbasis, that was this one here, of the UL and the lambda L. So this means P is sum for the eigenbasis, whatever I use for the eigenbasis L, of the eigenvector UL. And here, of course, comes now my projection of my vector P onto UL. P, T, UL. So, and now I can calculate this thing. QP is PT, those who are sort of more in training with linear algebra will already have guessed what we will get in the end. We now put this in here, put our sum here over VL. These scalar components go to the front. T, T, U, L squared. And then we are simply left with UL T, Y, T, Y, UL. But this here is, of course, lambda L, UL, because you remember in the U's were the eigenvectors of the matrix. Yeah?
You mean the eigenbasis of YTY?
Yes.
Wait, is it?
YTY LEQ. In a way, this is a bit maybe Q as a quadratic form also has an eigenbasis, which is of course simply defined as this eigenbasis. But yeah, that's what I mean. You remember, my Q of P is just the abbreviation of P times the matrix times P. So, now exactly, because this is the eigenvector of this is lambda LUL, so we now get that this is sum over all L, the projection of T on this eigenvector times lambda L, and UL is of course 1, because these are often not, these are eigenvectors of length 1, so we will multiply them by negative 1. Yep.
I imagine it's due to orthogonality. I was wondering, shouldn't we have cross terms? Because we have a sum over L, PT, UL, as in, to shorten the notation, we have PT, YT, YP, right?
Yeah.
We have two sums, one for the PT at the beginning and one for the P at the end. And so I would have expected there to be some cross terms.
Wait, you don't have the cross terms here because they cancel out, but I don't know if it's immediately explicit that they cancel out or not. Yes, we have to, exactly, what we do, if we do it properly, Yes, let's write it properly. Equals L, comma L prime. Now comes from the left the PT U L prime times U L T Y T Y we need more space. Need to write smaller. P T U L U L prime. So this here is the left PT. Then comes YTY, and then comes the right PT, UL, and PTUL. So, and now you see what's happening here. This here, because of the eigenvalue relation, gives lambda L UL. And now the cross terms vanish, because here we have UL prime and here we have UL. But these are eigenvectors, and we have an orthonormal eigenvector system. So these things multiply to 1 when it's the same eigenvector, and they multiply to 0 when they aren't. And hence, we drop one of the two components and are now left with one L. And now L and L prime are the same. PTUL times lambda L. And this is our result, how we can evaluate the quadratic form with this thing here. Now you can also see why it's called a quadratic form, because if we change something in the vector, and hence this coefficient here, which tells us what the vector does, if we expand the vector in the eigenbasis and then change anything like multiply it with something, then everything here gets squared. So in that sense it's quadratic. So, and now coming back to our question, which P1 maximizes QP1. And we can quickly look at this and wonder, which P do we want? Let's say let me to make it a bit nicer, call this here rho L U L. So I introduce here this rho to call these coefficients here, which are the expansion coefficients. Then I can also write this here in a little bit less annoying form by simply saying this is rho L prime U L rho L prime U L prime T Y T Y U L rho L. And then I can write this here simply as rho L squared lambda L. And now I want to know which P1 maximizes QP1. And of course what we want to have is we want to have a P1 with unit length. Because otherwise we just say, well, let's just use an infinitely long one. So we want that P1 has length 1. Otherwise it's cheating. We're trying to find the basis, so we're trying to find unit vectors. Remember, P is the basis of our subspace. So this means that the QL cross squared, that the rho L squared add up to 1, because this is our coefficients in the orthonormal basis done by the eigenvectors. And so we have to put all our rho L squared, we have to make this matrix, this sum here, as big as possible by putting different values here for the rho L squared, which add up all to 1. And when the answer is obvious, we have to put all our weight into row 1 and nothing into the rest. So the maximizer, which maximizes this thing, is row 1 is 1 and row 2, row n or whatever is 0. Because whenever I put something away and put it here, it gets multiplied with a smaller eigenvector, but I want to get all my weights here in front of the biggest lambda L. And the biggest lambda L is of course the first one. Because, as I forgot to say here when I wrote down my eigensystem, this eigensystem is as usual of course sorted. Now we have our solution. The subspace should go into the direction of the first eigenvector that we have. Let's write this here. Optimal 1D subspace Doppelpunkt use U1 spaces. And now, what about k equals 2? If we want a two-dimensional subspace, then what we have to do is when we have to choose a second, when of course the first one is, we still start with P1 and now we have to choose a second basis. We keep P1 equals S1 and find a P2 which is orthogonal to P1. And then we have to think about what is the best we can do for P2. So how do we optimize? So we want to optimize now this time this QP1 plus QP2. Because, as you remember, our original thing is we want to maximize the projection stuff, and the projection stuff we have said the sum of all the norm of all the projected vectors we have said can be written as this sum over all the basis vectors of still there. Let me check for a moment. Tennis racket theorem ISS. See if we find this famous thing here. In English it's called the tennis racket theorem, in German it's called the Zanibekov effect. What you see here is I think this is the Mir station, you know, the old Russian space station from before the ISS. And he tries to demonstrate what I can't quite demonstrate. If I rotate this thing around the intermediate axis, it starts to tumble, but unfortunately it falls down before you see it tumbling back and forth. But if you do it in zero gravity, you see this weird happening here, which is, I run it again, really weird. If you want to know where it comes from, it's called the intermediate axis theorem or tennis racket theorem, because the best way to demonstrate it on the ground is by throwing a tennis racket, and it goes a bit more deeper into this eigendecomposition. But for our data, it also only applies to 3D, and our data is 100-dimensional, so we don't have this now. What we instead do is that we have now a quick look at our actual PCA data from the Big Five. So let me see, where have I put this? Here. So what I did here, where is this page Open Psychometry? And in this page, we allow you to download a big data matrix from where they made a questionnaire with questions from this thing and asked simply online people to fill it out. And when you do that, when you get this big matrix here, where here this is what you get with some information about sex and source country and so on, and then answer to 50 questions. I took this out here, the 50 questions, and here is the answers of the subject to these 50 questions. And I quickly show you what the 50 questions are. tilde/downloads /big5 codebook. Here are the 50 questions. And these questions, they are not the kind of questions they used to establish the Big Five. It's something that they did post hoc many years after the Big Five were established. They then tried to find among the long list of questions those which seem to have loadings in only one of the Big Five components. So which seem to really influence mainly one thing and none of the others. So here the first 10 are questions which are all geared at querying extraversions or introverts to extroverts. And if you look closely, some of them are just in order to confuse the subject, to confuse the test subject, that they don't notice too quickly what's headed at. Some of them are inverted. I am the life of a party clearly has an agreement by extroverts, while I don't talk a lot, it has an agreement by introverts. We call this the inverse keyed questions, which are made such that those of the opposite end say agree. The next thing is neuroticism. 10 questions about how people are, whether people are sort of relaxed and stable or whether they're easily worried and anxious. Then A is, what's A? Forgotten. Somebody can guess from what's in here. The Big Five. Agreeableness, exactly. Where you can do well. Then we have conscientiousness, which is whether people are sort of taking care and are careful and orderly and so on. And finally, openness. That are the adventurous people versus the people who want to stick in their little world. So, this makes it a little bit of a bad example, because in a way there's the answer already in the data. I would have liked to have an example data where we also have mixed questions which query several things at the same time. I asked ChatGPT to suggest a few because I couldn't find him. Suggested things like untidiness makes me uneasy, which is a good example for something which both is a bit neurotic and a bit very conscientious. So let's look at how this data looks like. The first what I know is I do this PCA analysis. So this function PCA does the following. It takes the matrix, why did I say scale is true? It centers it, which means it subtracts from each question the average. That's what I said before about that we want to see that the value 0 is that these are no longer values from 1 to 5, but values where such that negative and positive is balanced. So we simply take the average for each question, subtract it from the respective row, and we divide them by the standard deviation. So with questions where everybody answers about the same and questions where people disagree wildly will be brought onto the same scale and have the same chance of influencing the outcome. And then it calculates the covariance matrix, the matrix transpose times the matrix, and then performs the PCA. And what it gives out as a PCA is this here. Here in center are all the averages which it has subtracted. In scale are the values by which it has divided them afterwards to bring them all onto the same standard deviation. SDEF, these are the eigenvalues. And when we have these two things here, the X matrix is the result of a projection, and the rotation is the one which rotates us from our S, which, as you might remember, sits somehow in a slanted way in the big space. And in order to really read off of things, we have to put a basis into this S, so that we can read off things. So X here is when the expansion of each subject's personality among the bases. And rotation, and we will see later why it's called rotation. Rotation is the matrix which contains the basis vectors for the 5 personality things. But as you can see, it has calculated not 5, but all 50 eigenvalues. And let's have a quick look at these 50 eigenvalues. And here you can see there is 1, 2, 3, 4, 5 big eigenvalues. And you can argue whether you might want to add the 7th and the 5th, the 6th and the 7th, and then the rest seems to be all sort of noise because we are nicely working like this. So let's assume we don't know yet what the whole thing is heading at the big 5 and take the first 8 because we think we take everything up to here. So as you can see here, what I now do, I take these, I look now at the basis expansion. These are the loadings which tell us for each of the 8 putative personality traits how much influence they have onto each of the questions. And because we had this inversing where some questions are scored backwards, I take the absolute value so that I don't get confused by this, and I plot this in this image here. And now you can already see what we have here. The rows in this matrix, so this is now the rows in this matrix are the questions, the columns are our 8 top principal components. And as you might remember, here are the questions are already pre-sorted according to what they are supposed to query, and in fact we can see the first 3 seem to have the first principal component seems to mainly have weight or loading on the extrovertedness, the second one on neuroticism, the fourth one on openness, and the third one and the fifth one, they seem to be sharing conscientiousness and agreeableness. And that's exactly what you said before. No, it's gone. But what he said before, or was it you, about what happens if the 2 eigenvalues are similar. These aren't even that similar, but it still has managed to somehow confound them a bit and hasn't properly moved it out. But what we can now do is that we say we now choose this 6-dimensional space up to here. And within this 6-dimensional space, we now try to rotate our basis and try to find a better basis, which is better in the sense that in each direction there should be a few strong loadings and a lot of weak loadings. And a guy called Kaiser suggested, let's just try out many different basis rotations and choose the basis rotation such that the variance of these columns squared is maximal. Because the variance will be maximal if a lot of weight is on a few, and it will be minimal if the weight is smeared out over the whole column. And that's what this Varimax thing does. Where was my Varimax? Here. I say, take this thing, which remember, you can read this here as the loadings, the influence of these 8 putative personality traits on the answer to the 50 questions, but you can also say each column here is a direction in question space, and the span of these directions is our hyperspace S. And in this hyperspace S, we now assume the projections into this hyperspace S are now our personality, and we imagine the first 6 or 7 of these dimensions might be useful, and the rest just collects noise. So if we now take this first 7 and ask what is the optimal basis, then maybe the basis spanned by the eigenvectors is not optimal. We could transform the basis and try to find a better one. We keep the space fixed within the span of these first 6 vectors, but we rotate the basis. And we find the basis that maximizes this rotation, and then we get this basis here. And now it worked much better. After we do this basis rotation, we clearly see that each component is associated with one vector. The last thing that I want to show you is what is this yty actually. We always said we have to make an eigendecomposition of yty. And as I told you, what this yty actually does, it is a matrix which contains the scalar product of each row of y with every other row of y. So it contains it is a matrix of a scalar product of the answer of every question with the answer to every other questions. And two questions which are associated with the same trait should have a high correlation, and two questions which are not associated with the same should have a low concentration. So I do this now here by taking this here is it with yty. Well, let's take it here, B5, and I use the correlation operator. The correlation function does what we want. It takes the matrix, centers and standardizes it, and then it multiplies each vector with every other vector. If you look at the formula for the correlation coefficient that you might have learned at some point, you will realize in reality the correlation coefficient is exactly this. You give it two vectors, it standardizes the vectors, i.e. subtracts the mean from both, divides them by the standard deviation, and then it takes the scalar product. That's what the correlation is. So it's precisely our yty vector of which we took the eigendecomposition. That was the matrix of the correlation of every question with every other question. And let's look at this, how this looks like. And here is the matrix of correlations. And as you can see, we have strong correlation of each question with questions from the same group and weaker with the other ones. You see this checkerboard pattern, which comes from the fact that some of the questions are inverted, so the correlation is negative. Now, if you look at this, you might say, why didn't we need all this PCA? If I just had looked at this correlation matrix from the beginning, I would have immediately said, yes, there's 5 groups. But remember, these questions have been post-selected after people already knew what the big 5 are, and furthermore they are sorted. First the 10 E questions, then the 10 N questions, and so on. I shuffle them here by making here with this O, with this shuffling command, I shuffle the numbers from 1 to 50. Here's a random permutation of a number, and now I reorder the questions. And if I reorder the question in this manner, so wait a second, B5M, the questions are the rows. Then, are these the rows or the, this is, I think, how I have to do it. Yes, let me write it correctly. Have it in. Yes. So here I take my B5M, and with this comma O, what I explicitly do is, as you can see, I shuffle the question. And now with the shuffled question, the correlation matrix looks like this. The block structure is vanished, and recovering the blocks from this thing seems impossible. But your eigendecomposition does exactly this. If you do an eigendecomposition on this thing, it recovers the block structure. So in that way, this is what the secret of the eigendecomposition. It finds the actual underlying structure in something by finding a basis in which the whole thing is sort of nicely ordered. So, and now to come back to our original point, single-cell sequencing. What do we have here? In this example, we had all these questions which are all influenced by, and we said this question, the answer to this question can be predicted by a subject's personality vector, which just needs only 5 numbers. And just from these 5 numbers, we can predict with reasonable accuracy the answers to all these thousands of potential questions, if we know the question's loading. So if we know which personality vector, but once we know this, it's clear. And the crucial point is that this is because we assume that the space of all possible answers to our questionnaire, the 50 question, is actually not a 50-dimensional space, but only a 5-dimensional space. We have to find the subspace. And in single cell, it's the same. We have our cell with its 20,000 genes, but we assume that the internal state of a cell is much lower, maybe only 30-dimensional, and that hence the expression of all these genes can be predicted from knowing this 30-dimensional vector. So we can compress the information that we have from all the genes with a PCA into a small vector of only a few components, and they will contain all the actual interesting information that is to be seen in the expression vector, and will already push away a bit of the noise that we don't need. So the same way how this PCA probably turns our questionnaire into a 5-dimensional characterization of a person. And in this process, we seem to lose information because we do a projection, but we actually get a much more interpretable picture. And these 5 values are probably even a better description of what the person, how the person is than the whole set of all the answers, because we have averaged out random mood fluctuation about I've misunderstood this question or that one is strangely worded or whatsoever. In the same way, in single cell, we reduce our 20,000 dimension to 50, not only to have less data to work with, but also because we feel that this will increase our signal to noise ratio. And this, of course, is pretty general. You will see this technique of using PCA to enhance the signal and kick out the noise. You will see it in very many different, basically in all kinds of science which work with big data. PCA is always the very first thing that people try. And it's the easiest and it's very profitable. The main disadvantage of PCA, which we shouldn't forget, is it's a linear operation. Our fundamental assumption, which we did at the beginning, here is that our prediction, what the subject will answer to the question, can be constructed from the subject's personality in a linear way. And even for the questions, this is already an issue. You might ask questions, can imagine questions where nobody will really feel comfortable to completely say, I fully agree, but everybody will see I might agree a bit. And other questions where everybody immediately jumps to I fully agree. Or you might imagine a question where it's much easier, where you can fully agree, but you cannot fully disagree. And then the mapping from the personality to the question answer is no longer linear, but might be steeper to the positive and to the negative side. And if we do this, then if this is the case, then our PCA won't work well anymore. We can think about it. Maybe I make this a little homework where you try out what actually happens if you do this. What happens if one of the traits, one of the features is not a linear but a quadratic function of a personality vector? And then you will find this gives you fake additional principal component. This gives you an extra eigenvalue which then appears out of nowhere. But it works surprisingly well, this assumption that it's linear. You see here in this case it was not so easy to say whether we have 5 or 6, but I was really, but it's impressive how well we get if we look back at how well we could reconstruct from this noisy thing our 5 blocks. It would now be nice to see how this looked with the original data when we didn't know yet which questions to focus on and had a lot of things. Fortunately, I couldn't find any, probably because this was done in the 1950s, and at that time they still did it in punch cards if they didn't do it completely by hand. And yeah, don't have no punch card reader. Okay, so this was what I wanted to tell you about PCA. I might make a little homework where we do a simulation. So basically you come up yourself with a loading matrix where you say, let's imagine the people have these 4 personality values, and I have this matrix of a question. When you simulate what the people might answer, add a bit of noise and see if I can recover it. That's a useful way, because then you can try out how much noise can I add here before the thing loses
before the PCA doesn't work anymore, because I know what data I put in, can see if I can get it back out. And that's generally a good tool in scientific computing, so maybe we should try it. Okay, questions about this? Comments? Ideas? If you now want to know your own personality score, that I can show you as the last thing. So there's this website where I found it, Open Psychometrics, and there you can answer these 10 questions here. And then, of course, once you've answered them and you have all your scores, then you can download and look in the data that we've just played with and see where do you stand in comparison to everybody else. In order to then get your 5 personality values on this introversion to extroversion scale, you just have to run it through the PCA, do the rotation with this big multiplied with a matrix, and you will know your personality, at least according to this thing. To sum up at the end, what you will notice if you then look at the histogram of all the subjects' values on, for example, the introversion to extroversion scale, you will notice that the subjects are typically normally distributed, with most people in the middle. Most people are neither introvert nor extrovert, but somewhere in the middle. And that is the issue with all these popular pseudoscience personality tests. They always try to make a dichotomy. You have to, in your 4-letter code, you have an I for introvert and an E for extrovert. And that might be appropriate for those few percents which are in the tail of the courses. But all the people in the middle will be arbitrarily labeled one or the other, depending on where just a little bit to the right or to the left of a zero. And that's what generally happens. I mean, this, nobody likes an online test which tells you, yeah, actually, in most respects, you're just like everybody else. Even though this might be true, though they put in this artificial dichotomies by just cutting in the middle, where actually most people sit, and where cutting hence is most inappropriate. And again, this is a typical question which you have in data science and in working with real-world data, to dichotomize or not, to ask, should I keep my data continuous, or should I sort of divide it up into range blocks? And just dichotomizing right in the middle where everybody sits is not a good idea, and that gives you all this nonsense. But the actual personality thing has its truth, and to be honest, I find it pretty surprising that this PCA really robustly, over many decades of psychometry research, has always led back to the same 5 axes. What changed a bit is how people label these 5 axes, because they look at their question and say, okay, all these questions have a high value have a high loading for the first principal component, and all of them seem to be towards whether people like to be among others or by themselves. How should we call it? Let's call it introversion to extroversion. Maybe other people might call it, let's call it to private versus gregarious person and so on. So once you have a principal component, giving it a name is a completely new question, because now we have to look at all the questions which go into this PC and say, how then can we summarize this into 2 well-describing words? And you risk bringing in your own personal biases in these words. This is why people tend to go upset with the dimension N, neuroticism, because this is clearly a charged word. By introvert and extrovert, you will find a lot of people who say, I'm happy to be an introvert, or I'm proud to be an extrovert. Nobody is happy to be a neurotic. So we've always been discussing about whether we might find a more neutral term, but unfortunately it isn't. It seems to be something which is a trait which people consider bothersome. But yeah, I really like this Big 5 example, because it's a fascinating way how you can use math in a way where you would least expect it, namely talking about human personalities, and where in the end you get a solid result. And of course, it's a good way to get an intuition of what PCA actually does. Good, thanks for your attention, and see you either tomorrow or next week.
Ich würde noch kurz